This paper lays out the basis for a new technology that we hope will be important for fabricating machines at the micron to nanoscale. My group has been interested in the mechanics of origami structures, and recently Paul published a paper on using graphene to do kirigami. And so we got together and thought to ourselves, well, could we start to think about how to get graphene to fold up into geometrical shapes that might serve as scaffolds or the basis for machines at the micron and nanoscale. And so this is the achievement that Mark made. Was he made a bimorph, the world's thinnest bimorph, out of a single sheet of graphene and 2 nanometers of silicon oxide that was fused to it.
A bimorph technology where you have 2 independent layers of material. You introduce a strain into one of the layers relative to the other. That one wants to expand, and that leads to a bending for the total stack. Okay, so once we have the devices in our probe station, we have a series of robotic arms that we can use to poke and prod them. So here I've got one of these arms, and I'm pushing at a hinge. This is a graphene glass bimorph bent at 90 degrees, holding 1 pad vertical. And I'm coming in with my probe, and I'm pushing it, causing the hinge to strain, and then when the probe comes off, it releases that stored up energy. So one of the very cool things about working with nanoscale origami is that it's fast. Things can take place much, much quicker because the hinges themselves are so thin. And typically, the amount of time it takes in order to, say, heat a bimorph or push chemicals into it scales with the thickness.
Bimorphs that we make are completely compatible with semiconductor technologies. And this is one of the crucial, I think, thrusts that we wanted to focus on, because that means that these scaffolds can then later be interfaced with computer chip.
So what we're building is a kind of exoskeleton for the electronics, where the exoskeleton is made out of a 1 atom thick sheet of graphene and a tiny layer of glass on top of it, the bimorphs that you've heard about here.
In the nanofabrication facility here at Cornell, we could design a processor like the Intel 4004 that is small enough that it can fit on a machine, a device that we've made, again, at the CNF, that is 1/5 of a hair diameter. That means that you can put the computational power of the spaceship Voyager on a machine that is smaller than the width of a hair. And that is fantastic.